Okay, so we've developed a sort of novel episcopic fluorescent image capture device. It's automated, and basically what this does is allow us to capture the three-dimensional nature of the optic nerve head and the tissues, so we can input that geometry into models, computational models, to look at the effects of intraocular pressure on the mechanics of the nerve head. So you need to know what the three-dimensional geometry is, and you would typically use like a CAT scan or an MRI to get this kind of geometry, but this structure is only 2 millimeters in diameter in the eye, and there's no CAT scan MRI system out there with the proper resolution to get resolution that we need to do this. So what we've done is develop a system based on a microtome, a fluorescent microscope, a very high resolution astronomy camera, and some kind of nifty automated controls that allow us to embed an optic nerve head in some opaque paraffin, which is a standard histologic technique. And as we chop away 1.5 micrometer thickness of that block, we image the block face. And then we can stack those images up in space and create a very, very high resolution three-dimensional reconstruction, or a volume, that encompasses that optic nerve head. So you see here is the image that we're sort of imaging on the block face, and this is a cross section through that stack of images that shows you the optic nerve head. So this gives us a 6 millimeter field of view, so very large field of view relative to like a microscope, but at a very high resolution. So these images are 1.5 micron per pixel resolution at 1.5 micron per image depth. So we have, cubic voxels in our volume. Just to give you an idea about how good that is, a typical MRI in the patient's got about a 5 millimeter voxel resolution. So you're talking about maybe a little better, maybe 2 millimeters in the brain. So you're talking about something that's 1,000 times more volumetrically, maybe 10,000 times more volumetrically, more resolution than you would ever get in any of these sort of non-invasive imaging devices. So what we have here is a device that's fully automated. It will text me a text message if it has an error. It will send me this image every 100 slices to my email, so I can track it and let me know where it is. I can log into it, turn it on and off. So it's very fault tolerant and error resistant, and basically fully automated. So I'm going to start the system now, and you can sort of see how it works. So what it'll do is take a slice off that, see the microtome here, it's taking a slice off the front of the block, blows all the chips off the blade, the block, and the lens, and then we'll image the block face with this fluorescent camera. And that's running through this light source here. We have the ability to do up to fluorophore forces. It's an automated filter cube changer that we built for this device. This is a custom device. And we align the images using this laser displacement sensor, which basically tells us where the microtome block stops in space within about a 200 nanometer precision. So really, really tight precision. We have a mirror that's epoxied to the top of the block carrier, and as that microtome comes around, the laser displacement sensor queries the position of that mirror, and then it can stack these sections up. So this is the en face image, what it's actually seeing, and this is a slice through the image. This is a vertical slice, and this one's the horizontal slice. And so here you see sclera, retina, optic nerve head, lamina cribrosa, and all those things are what we assess in our sort of studies of age and race-related susceptibility to glaucoma, and how those things are related to intraocular pressure and fluctuations.